I'm Trent Parado, Public Affairs Officer for NASA's Science Mission Directorate in Washington. I'd like to welcome you to today's news conference to discuss the results of NASA's Gravity Probe B mission. Let me start by introducing our 5 distinguished panelists joining us for today's conversation. First, Bill Danchey, Senior Astrophysicist and Program Scientist at NASA Headquarters. Francis Everett, Principal Investigator for the Gravity Probe B mission at Stanford University. Rex Jevedin, President of Teledyne Brown Engineering Incorporated. Colleen Hartman, Senior Advisor at NASA Headquarters and Research Professor at George Washington University. And Clifford Will, Professor of Physics at Washington University in St. Louis. For those joining us online, you can find out more information about Gravity Probe B by going to www.nasa.gov. And with that, let me turn over the discussion to Bill.
Okay, today we are here to announce the results of the Gravity Probe B, or GPB, mission. Let me first start by recognizing one of our distinguished guests in the audience today. We're pleased to have His Highness Dr. Prince Turki Al Saud, Vice President of the King Abdulaziz City for Science and Technology. GPB is one of only a very few astrophysics missions dedicated to fundamental physics. The goal of Gravity Probe B is to precisely test 2 consequences of Einstein's general theory of relativity. The first one is called the geodetic effect, which is the amount by which space-time is warped because of the mass of the Earth. The second is called the frame dragging effect, which is the amount by which space-time is dragged around or twisted because of the Earth's rotation. The latter effect was predicted by Joseph Lenz and Hans Thering of Austria in 1918, only 2 years after the initial paper on general relativity was published. The Gravity Probe B mission measures these effects by observing the motion or precession of the axis of 4 gyroscopes. These are very precisely made spheres of fused quartz that were coated with niobium so that they are superconducting when cooled to liquid helium temperatures. When the gyroscopes spin up to about 5,000 RPM, they produce a magnetic field aligned with the spin axis, a superconducting effect known as the London moment. This precession is measured very precisely by comparison to a fixed reference star, so that the satellite points to during the course of its mission. The Gravity Probe B is an extremely well-designed experiment with many checks and cross-checks so that the measurements and their errors are well understood and reliable. Gravity Probe B is designed so that these 2 effects are separated. The precession in the north-south direction is caused by the geodetic effect, and the precession in the east-west direction is caused by the frame dragging effect. Gravity Probe B is the second NASA experiment to test general relativity. The first one, Gravity Probe A, was flown in 1976 and was led by Dr. Robert Fizeau of the Smithsonian Astrophysical Observatory at Harvard University. Gravity Probe A compared the elapsed time on 3 hydrogen maser clocks. 2 were fixed on the Earth, and 1 was flown in space for about 2 hours, confirming that a clock on the Earth runs slower than a clock at the altitude of the spacecraft, which is a consequence of the equivalence principle. This measurement was extremely precise, verifying the equivalence principle to about 70 parts per million. Gravity Probe B represents one of the longest-running projects in NASA history, with NASA involvement starting in the fall of 1963, when Nancy Roman, who's in the audience there, provided initial funding for the development of a relativity gyroscope experiment. Francis Everett, who has been the principal investigator of GPB since 1981, started with the project as a postdoctoral researcher in 1962. At that time, he assisted Professors William Fairbank, Robert Cannon, and Leonard Schiff with the proposal to NASA. Dr. Brad Parkinson played a key role as a co-PI and project manager starting in 1984, as did Drs. Daniel Debray and John Tourneur, who were also co-PIs on this mission. Over the years, Stanford had many excellent project managers, including Bob Farnsworth, Sasha Bookman, Ron Singley, Gaylord Green, Bill Benzie, and Barry Mulfelder. Dr. Mac Kaiser is GPB's chief scientist. 2 of our panelists played important roles during the development of GPB. Dr. Colleen Hartman was the program manager for GPB at NASA headquarters, and Mr. Rex Jevedin oversaw the development of the GPB spacecraft at the Marshall Space Flight Center. After Rex left the project management role at Marshall, Mr. Tony Lyons was the project manager, and Dr. Jeff Kajajak was the project scientist. Gravity Probe B has touched many lives during the course of its evolution. It started as a theoretical concept. Then it became a laboratory technology demonstration. After that, it transitioned to a flight mission, then to an operating mission, and finally to an extremely difficult phase of data analysis after the flight. During each phase, the Gravity Probe B team rose to the challenges that it faced, and it overcame all of them. We now turn to Professor Francis Everett, who will discuss the mission in more detail and the results that have been achieved. Francis?
You know, the scariest moment in a physicist's life is when he sees the apparatus going up into the sky and knows that the closest he will ever see it be to it again is 400 miles, and then he starts thinking of all the things that he ought to have done differently. And that experience came to me on 9:57 a.m. plus 24 seconds and a bit more on April the 20th, 2004. So, what is Gravity Probe B? Can we have the first slide, please? Picture a gyroscope moving in orbit around the Earth, and let's ask what happens. If we live in Newton's universe, where space and time are absolute, and you made an absolutely perfect gyroscope, a purely imaginary perfect gyroscope, and you point it at a remote point in space, nothing will happen. It will go on pointing in the same direction for all time. But Einstein's universe is different. In Einstein's universe, space and time are warped by gravity. And so we end up by handling these two effects already mentioned, the geodetic effect in the plane of the orbit. And what happens is the Earth distorts the space around it very slightly by its gravity. If you were in empty space, you would have a perfect 2 pi times the radius. Around the Earth, there's a tiny bit less. Now, you remember the circumference of the Earth is 25,000 miles, so you ask the question, how much less from the distortion due to the Earth? And it's 1.1 inches in 25,000 miles. So it's a rather modest distortion. And that's the first of the two effects that Gravity Probe B has measured indirectly. The measurement on the gyroscope, the effect on the gyroscope, is an angular change of the gyroscope of 6,606 milliarc seconds at this 401 mile altitude. And I'll come back and say what a milliarc second is in a minute. And that's after 1 year. The second effect is that as the Earth rotates, it drags space and time around with it. And to picture this, imagine the Earth immersed in honey. Then you can imagine the honey would be dragged around with it, and your pointer in the honey would be dragged around, and that's what happens to a gyroscope. So the Earth actually drags space and time around with it. Fine. So what is a milliarc second? A milliarc second is the width of a human hair seen at a distance of 10 miles. It really is a rather small angle. And this is the accuracy which Gravity Probe B had to achieve. Now, it's nice to go back to listen to something that Einstein said in 1953 in his book, The Meaning of Relativity. So I'm going to read this to you. These effects, and he's referring actually to the frame dragging effect, which are to be expected in accordance with Ernst Mach's ideas, are actually present according to our theory, although their magnitude is so small that confirmation of them by laboratory experiments is not to be thought of. Nice quotation. But thanks to NASA, we've done more than think about them, we've actually measured them. And could I have the second slide? So what you see here is the final results, and the drawing on the left shows the change in direction of the spin over the course of a year for the geodetic effect. In Newton's universe, it would be a straight line along the top, but you see for the 4 gyroscopes, you get the change, the same change. The much smaller frame dragging effect, you also see a similar change on the right-hand side, and when you look below, we have the numbers. The geodetic effect, the predicted relativity effect, is 6,606.1 of these milliarc seconds, and the measured result is about a little over a quarter of a percent of that. The frame dragging we've measured to a little better than 20%. So that's the results of the experiment, and we'll come back and say more about them later. So you stand back at this point and you say, well, why bother about testing Einstein? I mean, these theories were developed a long time ago. Haven't they all been established? We need to understand that Einstein developed 2 different theories of relativity. In 1905, his special theory of relativity deals with objects that are moving at very high speeds, close to the speed of light. And this is extremely well tested. You can ponder about philosophical significance, but as far as the equations and the numbers, it's incredibly well tested. General relativity, as we usually call it, maybe you should call it Einstein's theory of gravity, which came 11 years later. It took Einstein 11 years to develop this theory. It's his theory of gravity, as we've seen, and this is much less well tested. The experiments have really been few and far between that are quantitative experiments, so we know of effects and can see qualitatively that they may be correct. The problem is, the annoying thing is, Newton was much too successful in his theory of gravity. You can call that annoying, or if you were an experimentally minded person, you could say it's exciting, because it now gives us something to do that's going to be a challenge, whichever way. But whatever you take on that point of view, Einstein's theory is tremendously deep, because it's the basis of our understanding of the large-scale structure of the universe and astrophysical phenomena like black holes, gamma-ray bursts, jets from quasars, and so on. So we've managed to test 2 of the most profound effects of general relativity and do so in a new way. Now, the heart of this experiment was the gyroscope. Slide 3, please. That's interesting. We only see 1/2 of this picture, but that's fine. That is a map actually developed by 7 undergraduate students, which shows the out-of-roundness of this gyro rotor. You see it's in mountains and oceans. The highest mountain, if you blew this up to the size of the Earth, would be 10 feet. The other part of this picture that I had intended to show you, seems to have got lost, was a picture of the gyroscope housing itself, made of fused quartz. Possibly Rex Jeverdon will show you something. Yeah. But actually, we have it right here in real life. So here is the sphere the size of a ping-pong ball going in a quartz housing. We electrically suspend it. We spin it up by means of gas, get it spinning to 5,000 RPM, pump out the gas to an extremely high vacuum, and there we've got our gyroscope. Which brings us to the question of how do you measure the direction of spin of a perfectly round, perfectly uniform sphere which has no marks on it? And this is where superconductivity, the phenomenon discovered exactly 100 years ago this year, leads to its. What was discovered is that when certain materials are cooled to very low temperatures, they completely lose their electrical resistance. But they have another property that when you spin them, they develop a magnetic moment, a magnetic pointer in them, lined with a spin axis. Spin them twice as fast, it gets twice as big. Stop spinning and it disappears. Spin them in the opposite direction, it points in the other direction. Be that as it may, this, with the aid of some very interesting devices called superconducting quantum interference devices, all connected into here, gave us a readout which was able to read 1,000th of an arc-second change in spin direction in 10 hours of time. Amazingly sensitive. And in fact, the truth is the secret of this experimentation is because of two different technologies, space and low-temperature physics technology. Now you see the gyroscope there. Good. Well, let's go on, however, to the next slide, please. And there on the left, you see a 600-gallon thermos bottle, 600-gallon, 2,400 liters, developed by Lockheed Martin in close collaboration with us at Stanford, which managed to stay cold when it was up in orbit for 17 months and 9 days. Lockheed got a little bit of an award for this because they had only promised 16 and a half months, and they beat it by 23 days. And it actually turned out those 23 days were very useful. So not only does this make this readout possible, it did a whole number of other things in making this experiment, shielding the gyroscope, making the system mechanically stable. And it was the combination of the two is what counted. And on the right, you see, with a ball the size of a ping pong ball, and you end up with a spacecraft that stands 24 feet high, but with 4 of them in it. So how did this develop? We heard about the funding that was initiated by Nancy Roman and was developed for us in the laboratory. And at a certain point, after a time, you go through a major review process, and now we're ready to go to space. No, we're not. It's at this point you make the huge transition from laboratory experience to a flight program. And the key figure in accomplishing this, he's very sorry he wasn't able to be with us today, is Bradford Parkinson. He's got an unavoidable other commitment. But he had done his PhD on what related to gravity probe B. He then became an Air Force officer. He was an Air Force officer and became the Air Force colonel responsible for the development and flight of the first 4 GPS satellites. We used to like to tease Brad that he's just changed one letter, GPS to GPB, but whatever. Anyway, one learned an enormous amount from Brad, and one of the most interesting remarks he made 1 month after he joined us was, look, what we're doing here is a cross between an academic program and a Silicon Valley startup. And you've got to have both those mindsets to pull this off. After all, you're doing it in a university, and it better be a university program, but you've got to be serious working with industry and everything about how that gets done. And that was the challenge and the opportunity. In total, this program has seen 100 students winning PhDs, 86 at Stanford, 5 at the University of Alabama, Huntsville, 3 at the University of Aberdeen in Scotland, and others at other universities. There have also been 353 undergraduates who worked at it. I mentioned the work of the mapping that was done by 7 undergraduates. And we've had some very interesting high school students working with us. And I'm glad to say we got representatives of all 3 groups with us here today. Some of them are just a little bit older than they once were, but that's all right, you know. Now, there's an old established principle in experimental physics. Supposing you're worried about a certain error and you're not sure how bad it is, what you do is you deliberately increase it in some calibrated way so that you can determine how bad it is or how good it is, whether you're fine or not. And we had, in our last 46 days, 23 of them given us free by Lockheed, we had this calibration phase where we deliberately did various enhancements. And we discovered one serious effect of misalignment torque, a factor of 100 bigger than we had expected it to be. And this led us to a 5-year detective story. We actually discovered 3 different consequences of this, the one we found and then 2 others later. But we managed to catch the 3 criminals and lock them up, and that's how we got the results. And it's a heroic effort by the team, I would say. So in this, completing the data analysis was a large, hard grind. We Oh, enormous thanks to Richard Fairbank, with matching funds from NASA for part of it, to Vance and Arlene Kaufman, and to the Saudi Arabian Institute KEXT, not only for a certain amount of support, but also from some superb brains whom they brought to work with us at Stanford, for outstanding analysts. Now, Gravity Probe B is not only a new experiment, it's a new kind of experiment, and I don't want to over or underestimate that. You see, it's a controlled physics experiment based on exact measurements on orbiting gyroscopes, and several other important tests have been more astrophysical tests. Not ranking one against the other, but the great beauty of it is that we have complementary tests of general relativity. And so it was a big challenge, and I don't think we could have ever done it if it hadn't been for the great collaboration we had between NASA Marshall Center, Lockheed Martin, and Stanford University, and that's wonderful to have done that. So we completed this landmark experiment testing Einstein's universe, and Einstein survives. So now Rex Jebedian will say something about the technologies.
Thank you, Francis. Gravity Probe B, while conceptually simple, is a technologically extremely complex experiment. In fact, the idea came about 3-4 decades before the technology was available to test the idea, and that's the reason for the 5 decades history on it. Francis mentioned 13 novel technologies that were created for Gravity Probe B. I'm going to mention about a half a dozen of them here, but I'll say that special technology breakthroughs were required in every significant part of the experiment, including the science instrument itself, the science payload, and also the spacecraft. If you would, please bring up the slide that goes for technology. Francis has already talked about this exquisite quartz ball here. If I could borrow your prop, Francis, I'll give it back, I promise. These are thought to be the roundest objects ever manufactured. In fact, you can look in the Guinness Book of World Records and find that it's in there. The diametric variation across this sphere is about 0.2 of a millionth of an inch, so it's incredibly round, an amazing achievement. It's also very, very homogeneous. The center of mass needs to match the center of geometry of this to avoid any Newtonian torques. The equipment that was used to manufacture those balls, this lapping machine, was actually invented at the Marshall Space Flight Center and later refined at Stanford University. And by the way, Sasha Buckman, who's sitting in the audience here today, was involved, ran the gyroscope development for a good number of years. The gyroscope suspension system was another trick. This system not only suspends and controls the gyros at the beginning of the experiment, it also provides very accurate position information that's used to feed back into the spacecraft to enable the drag-free operation of the spacecraft. I'm going to talk a little more about drag-free in just a minute. And Rob Brumley, Bill Benzie are in the audience today. They were both involved in aspects of that gyro suspension and spin-up. The gyro readout system that Francis mentioned earlier, which uses these superconducting quantum interference devices to read this London moment from the spinning superconductor. This is an amazing set of technologies. I always think of the London moment as God's gift to Gravity Probe B. I mean, how do you measure the direction of this, the spin axis of this gyroscope without disturbing it? And we get that through the London moment. Barry Mulfelder, who's in the audience today, by the way, was involved in the squid development. One of the photographs that you see there, you can see the photograph of the telescope. Lab technicians holding that telescope. It's about 8 inches in diameter. That's a beautiful, breathtakingly beautiful, in my opinion, solid glass telescope. It functions as a star tracker in this experiment, and it's certainly the most precise star tracker ever conceived and ever developed. A typical star tracker looks at a field of stars and uses that to help the spacecraft to navigate. This particular one literally splits the star into 4 quadrants to provide very precise pointing all the way through the entire experiment. The science payload has its own set of amazing technologies. You saw the photograph of the Dewar earlier on. This giant thermos bottle, 600-gallon thermos bottle, kept the experiment at near absolute zero for about 18 months. That's about 60 degrees below zero Fahrenheit, by the way. And it was filled with superfluid helium. Inside that Dewar is a special technology that was invented on Gravity Probe B called a porous plug. And that porous plug, what it does is it controls the interface between the vapor and the liquid side of that experiment. In other words, it allows the helium to boil off as it warms up, but it keeps that superfluid inside the container. Superfluids want to crawl out of their container, and so managing that interface is a trick, and it took special technology breakthrough and a special material to do that. There's a payload feature called the probe. It's about a 10-foot long structure that's used, that goes down into the probe and interfaces the science instrument to the doer. One of the interesting techniques that we used was to let me back up and say gravity probe B has to be very magnetically pure. It can't be under the influence of magnetic fields or it'll mess up the superconducting readings. And so the probe has to block the Earth's magnetic field, but we also had to work on cleaning out any stray magnetics that would be inside the experiment, inside the probe. And that was done with this ingenious technique called flux flushing that involved cycling the temperature, literally trapping the magnetic flux inside of a paper-thin lead bag, and then pulling layers of that lead bag out of the probe, which enabled us to literally lift the magnetic contamination out of the probe. John Mester is here today. John was the magnetics guru back in the day. Later went on to larger responsibilities, but it was incredible technology and an incredible technique in that case. The spacecraft I already mentioned was a remarkable technological marvel. The gyros have to fly basically undisturbed, non-Newtonian torques, which means that you basically have to put the spacecraft into what is a drag-free orbit. In other words, it needs to be in free fall as it moves about the Earth. Any spacecraft at any altitude is going to experience some amount of atmospheric drag. Even at 400 miles, there's a very sort of a tenuous atmosphere, you might say. And because of that, you have to compensate for that drag in order to keep a drag-free type of motion to the spacecraft. And the way we accomplished that was to use the helium boil-off. That helium that was boiled off was used to power some tiny micro thrusters, and they controlled the spacecraft attitude and translation with forces that approximate that of a human breath. So you have this spacecraft just floating through space and this puff, puff, puff going on at about a tenth of your breath, actually.
Can I just interrupt for a moment? We are very happy to have George Pugh with us, who's the inventor of the concept of drag-free technology, and we should acknowledge him for that.
Thank you, Francis. So when you look at technology, and I haven't described all of these technologies on Gravity Probe B, but you think of technology as the application of science to some particularly difficult problem. But in the case of Gravity Probe B, there was an incredible sort of symbiosis between science and technology. The technology enabled the science. The technology that was invented led to new science. For example, this porous plug technology that I've discussed already, was the enabling technology, or an enabling technology for the cosmic background explorer, which accurately determined the universe's radiation background, and that's an underpinning for the Big Bang Theory, of course. And its determination led to a Nobel Prize for NASA's Dr. John Mather and his colleague George Smoot. And technology development within GPB led to numerous science breakthroughs. Dr. Everett's thesis advisor was the famous physicist and Nobel laureate P.M.S. Blackett. And he once said to Francis, I think, if you can't think of what physics to do next, then invent some new technology. And you will find some new physics. And indeed, that was the case on Gravity Probe B. I will have to tell you that as the former program manager of Gravity Probe B, I was often called upon to defend the use of public funds for something as esoteric as a measurement of Einstein's relativity. And I think the case for its defense is pretty compelling and pretty easy. I would always say, look, even if you're not interested in the science result, even if you're not interested in the educational result, this 100 PhDs and so on, then you at least ought to believe that the technologies that were invented in the course of Gravity Probe B's development will pay dividends, economic and scientific dividends for decades to come, enormous dividends. But even above the level of a practical or economic argument about it, I would say that when you take on something as challenging as Gravity Probe B was, and you're facing very long odds when it comes to the technology, very long odds when it comes to even succeeding programmatically, and you accomplish it, then I think it's a reminder of the sort of greatness that humans can get to when they put their hearts and minds on an objective like this. And so I think GPB GPB is about science, it's about technology, but it's also about a triumph of the human spirit in the end. With that, I'd like to turn it over to my good friend and colleague, Dr. Colleen Hartman, to talk about the history of GPB.
Thanks, Rex. 5 decades after it was first conceived, today we're celebrating the results of the Gravity Probe B experiment. Testing Einstein's most compelling contribution to humankind is not just a technological marvel, although Rex makes a rather good case for that. It's also an engineering and management case study that's worth a closer look. So my job is to give you a brief history of GPB. A half-century ago, 2 men had the same idea, to use rotating gyroscopes to test general relativity. And Dr. George Pugh, who is with us today, had the idea of using a gyroscope in space, in low Earth orbit, pointing at a guide star in a completely drag-free environment, so no other forces would impinge upon it. So basically, you have a rotating top that you look at its precession or how much it wobbles. He published his results in 1959, and he was working for the Institute for Defense Analysis, and he was an MIT professor. So this idea was published in a DoD publication. He also recognized in this publication the application that drag-free technology could have for us, including in areas of aeronomy, geodesy, satellite navigation, and modeling the Earth and other planets. Meanwhile, Leonard Schift had the very same idea, and he published his idea in 1960 in Physical Review Letters, the very same place where, 51 years later, today, we're announcing the test results of GPB that Francis and his colleagues are publishing. The 2 men learned of each other, and they did something rather quaint and old-fashioned, if you forgive me, Dr. Pugh. They wrote letters to each other, and eventually they exchanged manuscripts. So now we go up to about 1963, a couple years later, NASA begins funding Stanford to think about this idea. And that low level of funding goes on for 2 decades. To give you a passage of time, during that 2 decades, NASA launches puts men on the moon, launches a probe to Mercury, launches the Voyagers to do an outer planets grand tour and beyond, conceives of, builds and launches the shuttle, and begins to build the International Space Station. Then in about 1984, NASA actually funds Stanford to begin building the GPB experiment, and now it's a real project. At about this time, Stanford subcontracts to the Lockheed Martin Corporation for their aerospace expertise, and the Marshall Space Flight Center comes on board to add their engineering expertise to the team. The idea here is to make a shuttle test flight of some of the most important components of GPB for a shuttle acceleration environment, to be followed 2 years later by a shuttle flight of the Free Flyer. The 1986 Challenger disaster changes all of that. The plans are scrapped, and now GPB will go directly to flight on a Delta II. So in rather quick succession here, Lockheed Martin produces this giant Thermos Bottle, the Doer, the probe, the satellite. They're delivered to Stanford University. The experiment, this amazing 4 ping pong balls, if you will, coated with niobium that can be levitated or integrated in it. It's tested. It's shipped to Vandenberg Air Force Base, where it meets that 1-second launch window on April 20th, 2004, and has the regret of the PI then looking at it going away from him. After several more years of data analysis and data collection and excruciating data analysis, that brings us to the celebration and the event today. The last decade has seen the development of exquisitely sensitive instruments, new instruments that are able to probe our universe, and we have received surprise after surprise. When carefully tested, some laws that we considered sacrosanct, some laws of physics, have been found deficit. So the weakness of the gravitational force means that general relativity has not been as thoroughly tested as some other theories of fundamental physics. And that's why this test result is so important. Now, even given that, I would say to me the most important thing about GPB are the people who touched it and whom it touched, especially the students. And it really is a who's who of America. So I'm just going to name two. Sally Ride worked on GPB, and Eric Cornell was an undergraduate student on GPB. He did his senior honors thesis on it. And apparently he was so inspired, he continued in the path of physics to one day recreate an Einsteinian prediction of a state of matter, a Bose-Einstein condensate, for which he won the Nobel Prize. So let's return now to the thoughts of the most famous patent clerk in the world. I think he would be very proud of the tenacity of this group of researchers. And I also think that he said something of himself that applies to the researchers, scientists, engineers, technicians, and support staff at Stanford, at Lockheed Martin, at the Marshall Space Flight Center, and to my colleagues and friends of GPB here at NASA headquarters. Einstein said, "It's not that I'm so smart, it's just that I stay with a problem longer." So now I'd like to introduce Dr. Clifford Will, who is a physics professor at Washington University at St. Louis, and also the head of our external review board for GPB.
Thank you. Well, I first want to describe the role of the Science Advisory Committee for GPB. The SAC was formed in 1998 at NASA's request to help ensure that the final scientific result of the experiment would be of the highest quality. The SAC consisted of 6 eminent scientists, including 1 Nobel laureate, plus me as chair, all independent of GPB and each an expert in a specific area relevant to the mission, from low-temperature physics to data analysis to general relativity theory. 2 members of the SAC are in the audience today. Over a period of 13 years and 20 SAC meetings, each lasting 1 to 2 days, we reviewed the progress of the mission, we criticized, we suggested alternative approaches, and we vetted. We critically reviewed drafts of the just accepted physical review letter, twice. Our charge was to ensure that whatever result emerged from the experiment, it would be credible to the scientific community and that the way it was obtained would be clear and transparent. In the unanimous opinion of the SAC, the GPB team attained this goal. Indeed, in our opinion, the effort of the team in obtaining the result you have heard today has been nothing short of heroic. Faced with the discovery during the final month of post-mission tests that anomalous motions of the gyroscopes were being induced by stray patches of electric fields on the surfaces of the rotors and on the interior surfaces of their housings, they found truly ingenious and innovative ways to pool all the available data in order to understand and map out these anomalies. They did this so well that they could still measure the tiny frame-dragging precession. This detective story, as Francis puts it, is an excellent example of how physicists solve hard problems. Solving this problem is in part why it took over 5 years of data analysis from the end of the mission to reach the announcement today. I would like to remind everybody of the importance of testing fundamental theories of nature. Even though it is popular lore that Einstein was right, I even wrote a book on the subject, no such book is ever completely closed in science. As we have seen with the 1998 discovery of the acceleration of the universe, measuring an effect contrary to established dogma can open the door to a whole new world of understanding as well as of mystery. The precession of a gyroscope in the gravitational field of a rotating body has never been measured before today. While the result in this case does support Einstein, it didn't have to. Physicists will never cease testing their basic theories, whether in order to confirm them better or in order to reveal new physics beyond those standard theories. In some realms, the only place to do this, to carry out such experiments, is in space. This was the case with GPB. Another central aspect of the scientific method is the publication of the results of the research. The physical review letter that has just been accepted gives the merest outline of GPB and how the result was obtained. GPB will truly be completed only when the full details of the experiment are published in the open, peer-reviewed literature. Measuring the frame dragging effect caused by the Earth's rotation also has implications beyond our planet. The incredible outpouring of energy from quasars along narrow jets of matter that stream at nearly the speed of light is most likely driven by the same frame dragging phenomenon about which you have heard today. In the case of quasars, the central body is a rapidly rotating black hole. In my own current field of research, gravitational wave astronomy, the final in-spiral end merger of two spinning black holes involved truly wild gyrations of the body's spin axes and of the orbit, again driven by the same frame-dragging phenomenon. And these motions are encoded in the gravitational wave signals that we hope will be detected soon by laser interferometric observatories on the ground, and in the future by a similar observatory in space. So there is a strong link between gravity probe B and some of the most energetic and cataclysmic events in the universe. Thank you.
Thank you very much, Clifford. I'd like to go ahead and move on to the question and answer session, if I could. Just a reminder for those in the audience, we do have a microphone coming around, so just wait for that. And please identify yourself and give your affiliation. For those that are joining by phone, you can signal the operator that you have a question by pushing the *1 keys. And so let me just check with the audience and see if there's any questions to start. Yes, please, Frank.
Frank Boring with Aviation Week. I wonder if someone could give a little bit more elaboration on how the noise was worked out of the equation, and some idea of the degree of confidence that it was done successfully. Thank you.
So I should say on that.
Francis,
Yeah. First of all, we discovered two things, one during the science mission itself, gathering the science data, and second during this calibration phase. During the science gathering, we discovered that the gyroscope was gradually changing its direction, not of spin, but of its body with relation to the spin axis. It's like a football spinning initially about the wrong axis and then gradually becoming aligned or whatever. So we discovered that. Then we discovered that there was a disturbing effect from pointing off which you pointed off to other stars, and we were able to calibrate this as we pointed off to another star and get a reasonably good number. The very interesting thing on that one that came out was we could check the number in two different ways during the data analysis. Now, three sets of measurements of this misalignment talk, one from the calibration and two from the other tests within the data analysis process, all agreed very well to the accuracy needed in the experiment. The strangest of all of the effects rejoices in the name of the roll-pole-hode resonance talk. And here is the phenomenon you observe. We have a spacecraft which rolls to averaging things, and we have a gyroscope that's spinning. And as it spins, it goes through a certain kind of motion which is called pole holding. This is relation to the motion of the Earth's poles. It's analogous. And you were sort of watching 4 gyroscopes. At a certain point, very strange thing happened. Over a course of a day, maybe, one of the gyroscopes moved off to a new position and then settled down. Very surprising. And then another, you'd go on for a while, and then one of the other gyros would do something similar, not in the same magnitude necessarily, not in the same direction, but the same phenomenon obviously was happening. Jeff Kajojak at Marshall Center was a key person in reaching an understanding of this, and what he showed was happening is the slowly changing pole-hode period at certain points reaches a resonance with the rotation of the spacecraft. By the resonance, it's a resonance with something like the 123rd harmonic or something, which no normal physicists ever would believe that you get effects like that. But we were able to verify it, and finally, I like sometimes to say that GPB is a confirmation also of Newtonian mechanics, because we had complete Newtonian explanations of these effects, and the numbers came out right. I don't know whether that helps. I mean, I'm not really giving 5 years of data analysis in 2 minutes, but that's the feeling. Do you want to add something on that, Cliff?
Well, I think another thing that was important was, and this is the kind of thing that experimental physicists do, they take lots of data on a particular experiment, only a small fraction of which may be directly relevant to what they want to measure. But in this case, there was data taken having to do with the very small additional magnetic fields that these rotors obtained. And that data was, in some sense, housekeeping data or junk data that wasn't super relevant to the main mission. But at the end of the day, exploiting this data was really critical to modeling these strange anomalous torques in such detail that they could track the orientation of the spacecraft, or orientation of each rotor with a tolerance of a very small angle over the billions of cycles during which each rotor spun during the mission. So this additional data that was there, they managed to exploit in a really innovative way to thereby build a model that allowed them to take care of these anomalous torques.
Thank you very much. I believe we have a caller on the phone, so if we could go to Adrian Cho at Science. Go ahead, Adrian.
Hi, this is Adrian Cho, Science Magazine. This is a question for Professor Will. I'm wondering how the Gravity Probe B result compares to previous results. There was a result in 2004, an analysis of the Lagos satellites that reported a 10% precision measurement of frame dragging. So I'm wondering how this measurement compares to that measurement.
Right. So this experiment he's referring to is a measurement of the precession of the orbital plane of satellites that are orbiting around the Earth that are tracked extremely precisely with laser tracking. The phenomenon here is the same. It's the dragging of space-time due to the rotating Earth, which causes the orbital plane to also drag around. So I regard these two experiments as rather different ways to attack the same phenomenon. You're measuring how an orbit varies. GPB is measuring how a gyroscope changes. Each involves some complicated data analysis with other sources of error that have to be understood and modeled to get the final result. So they are really two ways of attacking the same underlying phenomenon.
We can just pause and see if there are any further questions in the audience. Yes, sir. We'll get the microphone to you.
Joseph Taylor, Professor of Physics, Princeton University. This is for Cliff or Francis. I'm just curious to know that whether the patch effect difficulty in the end dominates the 20% uncertainty on the frame dragging.
Yes.
Thank you.
Any further questions? Go ahead, Frank.
It's Frank Mooring again. For Rex Gevenden, could you hypothesize some of the or elaborate some of the lessons that may have been learned in developing this spacecraft that could be applied to future spacecrafts, particularly in the context of that quote that you gave about inventing technology to do more physics?
Well, one of the interesting things about the spacecraft that I sort of touched on here was the interaction of the payload with the spacecraft. I mean, normally we have a spacecraft bus that has some sort of generic spacecraft functions, and you put an instrument on there and do things with it. And there's some amount of interaction through data systems and such. But what was really interesting about this one is that the instrument itself was kind of the heart of the control system for the spacecraft. The gyroscopes providing direct feedback into the drag-free part of the system and positioning information and so forth. And the telescope, of course, being not only part of the science instrument but also a guide star. So I think this kind of strong interaction between payload and spacecraft is pretty interesting and might apply to future missions. Well, the things that I talked about, the tying of the control system between the spacecraft and the payload, and using an instrument for a navigation and control function instead of doing that independently on the spacecraft. I mean, it's a very unique case, and so I don't think it's generally applicable, but there are some interesting and subtle things there.
Okay, and with that, we're going to go ahead and end today's event. I just want to thank the panelists for their time today, and thank the audience for joining us. As always, you can find out more information about NASA missions and connect with us at www.nasa.gov. So thank you all for joining us today. Have a good one.